I have the pleasure of introducing Professor Andrew Forbes, who is the speaker for today's webinar. At the University of Witwatersrand in South Africa, where in 2015 he established a laboratory for structured light. He is a fellow of SPIE, Optica, and the South African Institute of Physics. He is a member of the Academy of Science of South Africa. He also serves as the editor-in-chief of the IOP's Journal of Optics. His impressive career is marked by several awards, including the NSTF National Award for Contributions to Photonics in South Africa, which was received in 2015. The George Foster Prize from the Alexander von Humboldt Foundation, which was received in 2020. And the SAIP Gold Medal, the highest physics award in South Africa. Professor Forbes' international recognition includes the Sansuli Award from Optica and the Korean Optical Society, received in 2022, and the TWAS Prize for Physics. He is the author of more than 700 papers in esteemed journals and conference papers with a Google Scholar H index of 67 and over 17,000 citations. His pioneering work in the field of photonics continues to shape the academic landscape and inspire future generations of scientists. Therefore, on behalf of all the RIOS members, I welcome Professor Andrew Forbes to this webinar.
So let me get straight on to the point. So as you heard, I'm at Wits University. That's in South Africa. It's in Johannesburg, actually. If you come to university, it's inside the city. In fact, last year we celebrated 100 years of the university, and a little bit to the left of this great hall, over here you find the School of Physics, and inside the School of Physics is my laboratory. And basically what we do is we play with structured light. And what do I mean by structured light? So what I mean is we try to tailor light in all its degrees of freedom. So we try to identify what degrees of freedom does light really have beyond the textbook. How could I gain control over those degrees of freedom? And with that control, how could I use it to probe fundamental physics, but also to enhance applications? And here what you see on the screen, hopefully, is a little video. It's an experimental video that's playing, and it's showing you control over the amplitude and the intensity and indirectly the phase of light. But you can mix degrees of freedom to gain even more exotic control. So for example, if I take two such beams that are controlled very nicely and I add them together with orthogonal polarization, so have a look here. Imagine I have a Gaussian beam and it's, say, right-handed circular polarized, and I add it to a vortex beam. It's a beam that carries orbital angular momentum. You can think of it just as a donut beam that has the opposite polarization. What will happen? I will tailor the light in the polarization structure. And in fact, with this particular combination, I have a beam that has every possible polarization state embedded into the field. And I can write this field in a very simple Jones matrix manner, just like we would teach our undergraduate students. And what you see is that the one component looks completely different to the other component. And that means I cannot factor out a common spatial mode. And so very often when we speak about these types of vectorial beams, we speak about their non-separability. You know, is it possible to separate the pattern of the light from the polarization structure? And because these beams are non-separable, we tend to, these days, write them in a very quantum-like notation. So here's a quantum state from your textbook, but now it's not really a quantum state, it's a classical state. And A and B that you see in the state here, they don't refer to different photons as they would in the quantum world. They refer to different degrees of freedom of the light. So basically, the classical beam here on the left is made up of 2 degrees of freedom, a pattern and a polarization, and they can be added in a way that controls the separability. So just to conclude, the little introduction, imagine I took two beams. Here I show you a different combination now, and I have only one of them present. Then I would have a completely homogeneous polarization structure. The polarization would be the same everywhere. And you could say that this beam is completely separable. In fact, I can measure this and give it a separability factor of 0. And then as I start to introduce more of the other components, the pattern changes. It becomes partially non-separable. And eventually, when I have an equal weighting of both, I have a completely non-separable beam. So this would be 100% non-separable. So I want you to take two things out of this introduction. The first is that I can tailor degrees of freedom of light in a very exotic way. And the second thing is that I could measure the properties of these fields in a quantifiable manner and tell you exactly what's going on with the degrees of freedom. And I'm going to come back to this a little bit later in the talk. Okay, so let's go to the topic of the talk. The topic is, can we communicate with distortion-free light? In other words, have almost error-free communication. And to do that, we need to make light that goes through a noisy channel without getting distorted. So here is a little cartoon of an input beam passing through a channel. It's a noisy channel. It could be living tissue or multimode fiber or the atmosphere or underwater, and it comes out distorted. And the question is, can I make it distortion-free? So the first thing that we all know very well from our undergraduate photonics is that if you have any nonlinearity in the system, it's definitely possible to do it. We all know about optical solitons in nonlinear systems. So to begin the talk, I'm going to cheat, and I'm going to cheat to go to my favorite nonlinear system, which is a laser. So one of the things we do in my group is we build structured light lasers. So here's my cartoon again of a laser. It has a back mirror. So this is a Fabry-Perot cavity. It has a front output coupler that will leak out a little bit of the light. And inside the resonator, inside the box, I'm going to do something so that it controls the light that comes out. And in my first example, I'm going to ask, can I use a laser to make self-correcting lights? So I'm not going to make a laser that gives out one pattern of lights. What I'm going to do is make a laser that gives out many patterns of light at once. In fact, in an array of beams. So the way I do this is I take my laser, and here again is the back output coupler, and here's the other side of the laser. And inside, I'm going to put a telescope, just two lenses. And you know, if you put two lenses inside a cavity, then what happens is that, there's a very bad echo suddenly on this line. But what happens is that the light bounces back and forward between the mirrors, and the telescope will simply image from one side to the other. In simple English, this means that almost anything would be able to laze in such a cavity. So at the back of this cavity, I'm going to put a metasurface. And the metasurface is going to have a 10 by 10 array of little metasurfaces. Each one, so there's 100 of these little elements, each one can act as an independent emitter. And if I zoom into what it looks like, then it looks something like this. Very nice nanostructured metasurface. And what it's going to do is it's going to create vortex beams, beams that carry orbital angular momentum, and let them laze through every one of these little emitters. But if I just did that, nothing would couple them together. So I need to do another trick. And that trick is to move the output coupler back away from the metasurface by a distance that's 1/4 of a Talbot distance. And for the students in the audience, if you've never heard of the Talbot effect, go and Google it. It's an amazing thing. Basically, if you have a periodic structure, you can get coupling between the elements if you're at the right distances. And so by pushing this mirror back, the telescope lets everything repeat, and this extra distance lets everything couple. And so out of the laser, what do I see? I see an array of 100 coherent beams, all of them carrying orbital angular momentum. So that's very nice, but where is the self-healing property? So next, what I'm going to show you is what happens if inside this meta surface, I have a little defect. So I'm going to introduce it with a little video. So if you look at the right-hand side, you see that every element of the array has got a twist of 1. If you look, it goes from yellow to purple once around the circle. But this little one here has got 2 twists. So it's a defect. But watch the animation on the left. As the light bounces back and forward around the cavity, the defect sees the value of the OEM of the whole array. And so it gets coupled together and it forces the defect back into the original array value. So if you do this experimentally, what you find is that eventually the defect comes out also at a value of 1, the same value as all the elements around the array. So this laser has the ability to self-heal itself even when there are some defects into the materials that help make it work. And what's very exotic about the laser is that the coupling is not to the nearest neighbor like you would think. In fact, the coupling is to states around a ring. And what is the radius of this ring? It's exactly determined by the orbital angular momentum of the light. So here I've cheated a little bit because I've used a laser with nonlinearity to make light that has the self-healing property. So let's go back to our question and say, is it really possible to make distortion-free light? Because, you know, even in a vacuum, light diffracts. And when it diffracts, you can think of that as a type of distortion. So let me give you an example of how the structure of light and using its degrees of freedom can overcome this problem. So here on the on the right-hand side, you see a flat top beam, a uniform intensity beam. And this is very, very useful for manufacturing and many applications. Now imagine I take a cross-section of the beam that I show you here in this yellow line, and I plot it at z equals to 0, so no propagation yet. I have a very nice flat top beam. But as soon as it starts to propagate in the z direction, look what happens. It becomes very, very complex. In fact, it doesn't stay a flat top beam for very long. And now what we have is definitely not a flat top beam. So what we would like to do is structure the lights to maintain the shape as it propagates. So how could we do that? So we can go back to the example I showed you in the very first slide. Here I have my Gaussian beam and this donut beam, but they have opposite polarizations. This means that when I add them together, I add their intensities. So what will happen? Well, very simply, the Gaussian fills in the hole of the donut, and because they are both modes of free space, then when they propagate without changing the mode. And so now I get a flat top beam that is shape invariant as it propagates. And what have I sacrificed to do this? Well, remember what I told you, this beam has got every possible polarization state inside it. So I have used the polarization as a sacrifice in order to get my desired amplitude and intensity. If your application was polarization sensitive, then this wouldn't work for you. But if it didn't care about the polarization, you can use 1 degree of freedom to gain control over another degree of freedom. And that's the idea behind structured light. So that then brings me back to the question. Okay, so we want to go through a noisy channel. We want to know how to structure the light to do this. Maybe instead of talking about all the lights, what we should do is talk about which degrees of freedom of the light are going to be affected by some noisy channel. And we'd like to make it so that it doesn't matter what the channel is. Can we find a degree of freedom that's always invariant? So a good place to start is with a degree of freedom that is definitely not invariant. So a degree of freedom that is not invariant is, for example, the intensity and the phase of light. So here, if you look at the top, I'm going to take some structured mode. I'm going to put it through a channel. Actually, this simulation is for atmospheric turbulence. And out on the other side, we get a distorted spatial mode. Nobody in the audience, I think, would be surprised to hear this. And what I show you with simulations at the bottom here is that it doesn't really matter what mode you choose. Donut modes or Hermite Gaussian or Ligier beams, they all come out heavily distorted. And you can confirm this experimentally. So on this slide, I show you experimental results for an atmospheric turbulence channel. Initially, I have a nice orbital angular momentum beam. This is the experimental image. If I measure the OAM, it has a value of 1. This means 1 h-bar per photon of orbital angular momentum. And now I pass it through some turbulence, and look what happens. It comes out very distorted. And instead of the initial 1, I have a whole spectrum of values. So this is not good if you want to do optical communication, because now you have lots of crosstalk. So if you go to the literature, what you will discover is that people have said, the problem is maybe the orbital angular momentum, but if we go to these vectorial beams that I showed you earlier, maybe it will solve the problem. And the argument goes something like this. They say the orbital angular momentum, so the spatial pattern, is definitely affected by, say, turbulence. But look at the polarization. Well, in the atmosphere, the polarization is not affected because the atmosphere is not birefringent. So the argument is that, well, maybe in this vectorial beam, that the polarization kind of acts like an anchor to keep the beam stable. So I want to tell you that's complete nonsense. That's definitely not true. And it's very easy to show experimentally. So on the left video, I have an orbital angular momentum beam of 1. And on the right, it's a value of 10, so 10 h-bar per photon. And what I'm doing is I'm increasing the turbulence as the video plays. I'm increasing the turbulence for both cases. And I'm measuring the Stokes phase and the amplitude on a camera. And you can see very, very clearly that both the amplitude and the phase of this vectorial beam is completely distorted. So there's no way that this argument is true. But something very interesting happens. So let's go to one particular instance of the turbulence. So here are experimental results for just one instance of turbulence. I have my initial beam, so it's 2 donut beams. They have opposite phases. Look at this one. It goes from blue to red clockwise around, but this one goes from red to blue. So they have opposite twists to their wavefronts. And when you add them together, you get a nice radially polarized beam. Now I pass this radially polarized beam through turbulence, and what happens? The amplitude for each mode gets distorted. The phase for each mode gets distorted. And so when you reconstruct the polarization pattern, it's also distorted. It no longer looks like a radially polarized beam. But there's something amazing that happens. Remember I told you that you can measure the non-separability of the beam. And what that's really measuring is how homogeneous is your polarization structure. If it's completely homogeneous, you'll get a value of 0. And if it's completely inhomogeneous, in other words, it changes everywhere, it gets a value of 100%. And both these beams have a value of 100%. And there's a reason for that. Initially, the 2 modes that I added in this vectorial sum, they were completely orthogonal. So their overlap, if I look at their overlap, it's 0. And now they get distorted through the medium, but the distortion maintains inner products. So to put that into simple English, the 2 modes that make up the beam are distorted in just the right way that they remain orthogonal. And because they remain orthogonal, what does a unitary channel do? It preserves inner products. So anything that's based on an inner product will be preserved. In this case, it's the vectorness. How inhomogeneous is the vectorial structure? And you can check that in the real world. So here we are measuring this vectorness. Remember, it goes from 0 to 1. So we start with a value of 1, and we let it run over a hot plate. So this is real turbulence. And then what happens? It stays basically at the same value. And to show you that it doesn't matter what the medium is, we now take the vectorial beam and pass it through a chiral liquid. There's no longer a phase change. It's no longer the atmosphere. It's liquid and it's chiral. So it's actually affecting the polarization degree of freedom. If we start with a value of 0.5, it stays at 0.5. If we start at 1, it stays at 1. So the message is that this vectorness, which is an indicator of the separability of the states, it remains preserved through very noisy channels. And in fact, the reason it stays preserved is for exactly the same reason that entanglement is preserved through unitary channels. So this was tested in the laboratory. We have now subsequently gone out into the real world to test it. So what you see at the top, this is a little photograph, and we sent a laser beam from one building on our campus to another one. They're 270 meters apart. So on this side of the building, we prepare one of these vector beams, but with a different level of this vectorness, this non-separability. And we send it across the channel, and then we measure on the other side what is the value. So look at we use concurrence as a measure, but you can think of it as the 0 to 1 measure of this polarization separability. And you see that we prepare 4 different values. That's the dashed lines: 25%, 50%, 75%, and 100%. And we let it run a long time. We've done this middle of the day and morning and night. And basically you can see that the experimental values stay exactly on the designed value. And if you zoom into a very small time scale, then yes, you see random fluctuations like you would expect, but the values stay exactly on the determined value. So this means that no matter what the channel's complexity is, this measure, which is how vectorial is the beam, we call it vectorness, this measure is completely invariant to the channel's noise. So now you can think to use it as a way to communicate. Because imagine I create different beams. Here are 4 examples, and I create them to carry different levels of the separability, from completely separable, so value of 0, all the way up to completely non-separable, value of 1. And what I'm going to do is I'm going to put these beams through a noisy channel. So here's my noisy channel. So what happens? Let's look at this beam over here. It starts out looking very nice. It goes to the channel. It comes out distorted. But now I don't care about the distortion, because I'm going to focus not on what the beam looks like, but only on this vectorness that the beam is carrying. So I encoded a value of 0.33, and out comes a value of 0.33. This value is invariant to the channel. So that means that if I switch turbulence on or I switch it off, the value shouldn't change. And that you can confirm experimentally inside the lab. You can't do this in the real world because you can't switch off turbulence. But just focus on one of the values. Let's say over here, I've prepared some value of this vectorness. And look at the 2 plots. One is with turbulence, one is without. There's almost no difference. It's as if the communication channel doesn't even see that there is a distorting channel there. And if you look at what you prepared from 0 to 1 and what you received, it's absolutely on a straight line. So now the only question is, okay, I have a range from 0 to 1. I can subdivide it. How many levels could I use? Could I use 1,000 levels or 100 levels or 10 levels? And what we think is that you can subdivide it up until the noise level of your detector, because now the noisy channel is not introducing any noise at all to what you're doing. So we've run such a test, and what you see is that if I compare it to orbital angular momentum, this is with no turbulence, and here is with turbulence, then after we have 11 modes in the set, then of course initially it's pristine, but as soon as you have the channel switched on, you have very, very high crosstalk. But compare that to this vectorness encoding. I can go all the way up to 50 modes. And what is the crosstalk? It's less than 1%. So this is a way of communicating that totally eliminates the channel from the equation. All right, So let's go back to my vectorial beam in the cartoon form. Remember, A and B represent two different degrees of freedom of the same classical beam. Imagine your laser pointer. I prepare this beam here on the left, and it's made up of these two different degrees of freedom. It looks mathematically like an entangled state, but there's nothing quantum about it. Okay, now you say, well, look, if that worked so well in the classical world, why don't we use it to communicate in the quantum world as well? So could we replace degrees of freedom A and B with photons A and B? In other words, two entangled photons, A and B, and we send them to opposite ends of the room, and maybe one of them we send through our channel. Could we use this vectorness as a way to encode? And unfortunately, the answer is no. And the reason is that if I change the degrees of freedom to actual photons, if I go from classical to quantum, then I can replace the word separability with entanglement. And so as I sweep the C value, this vectorness, from 0 to 1, what I'm now doing is sweeping from a state that's got no entanglement of 0 to maximally entangled when it's 1, and then some entanglement in between. So of course that's no good. If you're doing a quantum communication channel and your entanglement is sweeping from nothing to maximum, your security will be compromised. So unfortunately, this technique doesn't work for quantum. To make it work, we have to look for something else inside the state that is invariant. And I want to show you something that we've been working on quite recently that takes this type of idea across to the quantum world. So let me go back to my cartoon that I showed you before. It's the beam with every possible polarization state inside it. So here it is, just the intensity map with all the different polarization states. Great. What I'm going to do now, just for visualization, there's no physics necessary here, but just for visualization, I'm going to replace the polarizations with little vectors, little arrows. For example, if it was right circularly polarized, I could give it an arrow pointing upwards. If it was left circularly polarized, I could give it an arrow pointing downwards. And now it's just for visualization to see that I have a spin textured field. Now remember, this field has got every possible polarization state. So if I map it to the Poincare sphere, that is the sphere that describes polarization, what will I find? I will find that I wrap around the sphere once. In fact, I wrap it completely once because the sphere describes all polarizations, and I have all polarizations, so therefore I wrap the whole sphere. And if I monitor not what the pattern looks like, but just how many times did I wrap around the sphere, then this is a topological invariant number. It will not change when you distort the field. And I think if you know anything about topology or you've ever Googled it, you've probably seen this little coffee mug animation. And basically what it says is you can smoothly deform a coffee mug into a donut. And so if you're looking for a coffee mug, you'll definitely see a distortion. But if you only count the number of holes, then you see the coffee mug has got one hole and the donut has got one hole. So this is a topological invariance. If I go back to my field, what does it mean? It means I can stretch or squish or deform my field, but that won't change the fact that I still have every possible polarization state. And so it will still wrap everything once around the sphere. So in our lab, we do a lot of quantum experiments in addition to laser and classical experiments. And so what we have done is we've actually created an entangled state with two photons. So now it's photon A and photon B are two non-local photons. And photon A lives in a spatial world, a world of space, because it's spatial modes. Photon B lives in a world of polarization. Remember, it's going to live on the Poincare sphere. So it lives in a world of polarization. So what happens? Imagine I make a measurement on photon A over here. I measure somewhere in space. Then it collapses the state of photon B to a particular polarization. If you were thinking classically, you would say, if you measure the beam over here, you will find a particular polarization, which is this one. But these are actually entangled states. So if I measure everywhere in space on photon A, I will collapse photon B to every possible polarization state. And then I have my topology. So the question is, where is the topology? So the topology actually sits in the entanglement between the photons. So the spatial structure of photon A is the probability of making a measurement, of getting a click. And when you get a click, it collapses photon B to a particular polarization. So if I measure everywhere here, I find a topological state, like a spin-textured state, that sits inside this entanglement. And I can stereographically map this to a sphere, the Poincare sphere. So that's what I've done here. And these little arrows then represent all the different polarizations, and they are wrapping all the way around the sphere. So this is conceptually how you would make a non-local topology between the entanglement of two photons. And if you go to the lab, then this is what you see. So the little arrows are the experimentally reconstructed topologies. You see that they're mapped to the spheres, and the red shows you the probability, the measured probability now of having got a click on the entangled states. And you don't have to worry about the details. Basically what it shows is that in fact I have all these topologies. I can wrap once or twice or 3 times around the sphere, and I have quantum topologies in polarization and space. So the question is, okay, but where's the distortion-free nature here? So have a look at this plot. On the horizontal axis, I'm changing the fidelity of the state. If you don't know about quantum, then it's very simple. What I'm doing is I'm deliberately decreasing the entanglement. I'm starting with a perfectly entangled beam, 100%, and I'm deliberately making a perturbation that drops the entanglement down to the classical limits. And while I'm doing that, I'm monitoring this wrapping number. And what you see is that if it starts at 1, it stays at 1. If it starts at 3, it stays at 3. So this topological invariance stays absolutely constant, even though the entanglement is decaying, and it only collapses when the entanglement itself disappears. And it's the same if I switch the lights on in the lab. So purity is a measure of how bad does the state get if you switch on the lights. So here it's perfect. I switch on the lights, it gets worse and worse and worse. But if I watch the wrapping number, which are the experimental data points here, absolutely unchanging. So what we have is quantum information resilience, even when the quantum entangled state itself is very fragile. So this is a form of quantum topology, and it means that there are properties of the quantum states that you can exploit that will not be distorted through a distorting medium. So we think that it's a very exciting field to pursue. We have many, many open questions. And if you want to know more about it, the work should be online in maybe about a month's time. So look out for the paper. Okay, up to now, I want to wrap up my talk with one final example, because up to now, I've always found some degree of freedom or some property of the beam that was invariant. But the question is, could I make the whole beam invariant to any noisy channel? So to answer that, let's go back to our flat top beam and ask ourselves, why did this work? Why is it that the flat top beam could stay flat top everywhere, even though usually it would change very fast? And the reason is that we found the eigenmodes of the channel. Well, in this case, the channel was just vacuum. But we found the eigenmodes and we added them in a very special way so that this could happen. So now what I'm going to do to answer the real question, which is, can I make the whole beam distortion free, is if I look at my original picture, I always focused on the beams. I focused on the input beam, and I focused on what came out. But now what I'm going to do is I'm going to ignore the beams completely, and I'm going to only focus on the channel. And I'm going to ask a very simple question. If I imagine my noisy channel as an operator, what are the natural eigenmodes of this operator? So now, if I phrase it like that, it's basically an undergraduate linear algebra problem. The channel acts on a vector and produces another vector. Think of it as a matrix. My channel is a matrix. It acts on some beam or some vector. It gives me a new vector. But if I find the eigenvectors of this operator, then what happens if the matrix acts on its eigenvector? Well, a matrix acting on its eigenvector returns the same vector. And in the language of optical beams, it means that the channel acting on its own eigenmode will return its own eigenmode. In other words, the eigenmode will go through this channel as if it doesn't have any distortion at all. And you can confirm this experimentally. So we've done this for atmospheric turbulence. And what do we see? So on the left, I have the eigenmodes of one instance of turbulence. And on the right, I'm comparing it to the orbital angular momentum beams that I've been speaking about throughout this talk. Let's just pick one example. Let's look in strong turbulence. Look at this mode over here. This is the input eigenmode. Here is the output eigenmode. You can see that they're very, very similar. And sometimes even the little smudges, look at this beam, you think, this little smudge in the middle is not real, but it is real because it comes out exactly with that smudge. So the eigenmodes themselves look quite distorted, but they are transparent to this medium. Compare that to the OEM modes. Initially, absolutely beautiful, but after the channel, very, very distorted. And you can quantify this with a crosstalk matrix. So if you put in OEM beams, then afterwards they come out very distorted, and so you have a lot of crosstalk. Do the same thing with the eigenmodes. Well, they look distorted, but actually they're the right modes for the medium, and so when you do the crosstalk matrix, you have zero crosstalk for the system. And so what this means is that it is possible to make distortion-free lights that passes transparently through the medium. And this should be able to be generalized to any medium that you like. So just to close the loop of the story, because I started with lasers, you might say, but what if you didn't know the physics of the medium so that you couldn't work out the operator? What would you do then? So here's my cartoon of a laser again. And remember what I told you, the laser bounces light back and forward, and then it finds the stable mode as the output. In another language, what the laser is doing is it's finding the natural eigenmodes of the cavity. Those are the modes that are stable. So in fact, if I go back to my structured light laser and I put in the medium that I don't know the physics of, and I let it laze, then the solution will actually be the output light from the laser. So this just makes us think a little bit differently about lasers, not as generators or producers of lights, but as complex problem solvers, systems that solve very complex problems. So to wrap up my talk with a few end notes, in my group, we play with structured lights. Orbital angular momentum is always our favorite mode. Here you see Angela producing some orbital angular momentum, but maybe it's not always the best depending on what you're trying to do. If the talk was a little bit too fast or a little bit too technical, then let me give you a sneak preview. If you're a member of Optica or you read Optics and Photonics News, it's the glossy magazine that comes out every month, then have a look out for the December issue, because there's a short story about how to make light distortion-free, and on the cover of the magazine is our funky sort of image of distortion-free lights. Then I have just a little bit of thanks to give. We love to collaborate in my group with groups all over the world. For us, it's one of the great joys of science is to be able to talk to people from different places with different ways of thinking, different ways of doing things. So please reach out to us. We do love to collaborate. And of course, all the beautiful results you've seen are from my students. We're a team of about 10 to 15 people, varies a little bit from year to year. And we love to send our students out to other labs. We also love to host students to our lab. So please do give us a call. And of course, thanks to them. And then finally, once again, thank you very much to the organizers for putting together this essentially month-long event. And thank you to the people who have stayed to listen.